H2 has no permanent dipole moment, so it's microwave inactive. There we go. And so this is active and this is inactive. So just keep in mind that some molecules will provide us information with microwave radiation, others won't. There's also a specific selection rule. And that is that delta J is +1 or -1. So those molecules that are microwave active can absorb or emit radiation, but J can only change by 1. So notice that +1 will correspond to absorption, and -1 to emission. Okay. So cool. So we want to think about the rotational energy levels, and then we want to think about the transitions. You absorb light, you go through a transition, and then we want to think about how that's related to properties of the molecule, and it will be related to the equilibrium bond length. So we already have an expression for rotation, right? Now, when we were talking about electrons in atoms, then we used the quantum number L, little l, as the rotational quantum number, and m sub L as the z component, the quantum number for the z component of rotation of the electron. If we're talking about the rotation of a molecule as a whole, we're thinking mainly about the nuclei, but it's really the molecule as a whole, then the same energy expressions apply, but convention is to use the letter capital J instead of the letter little l. Okay, so we have a rotational quantum number. So we're thinking about, just to make it a picture, some molecule and there's some axis and it's rotating about the axis, right? And it can have non-zero and zero components. So the energy expression we learned was J times J plus 1 h bar squared all over 2I, where I is the moment of inertia. And remember, I is mr squared, where r is the equilibrium bond length for the molecule. So we already know that. And before, as I said, we used little l, but now we're replacing that with capital J. So that is cool. Now in spectroscopy, we tend not to use so often units of joules, and instead we tend to convert to units of reciprocal centimeters. I'll explain why in a second, but right now, just as a definition, we're going to calculate E divided by hc, Planck's constant times the speed of light. And let's see what that's going to be. And we generally just do some algebra to simplify this. So, yeah. So this becomes h over 2 pi squared, all divided by 2I hc, and things cancel out. And what you get is h over that's what that becomes. All of this together we simply call B. I put a tilde on top to indicate that the units are not going to be energy. They're going to be whatever these units are. And these will turn out to be 1 over length. And we usually convert to 1 over centimeters, reciprocal centimeters. This is now called the rotational constant. And it's simply a constant, it has a given value for a particular molecule, right? Yeah. Now, we're going to give a name to this ratio, the energy divided by Hc, and we're going to call that F, and you'll notice that F depends on J, and we usually write it that way. And we call this the term. This is the rotational term. This is the energy, obviously, we call this a term. Notice the nomenclature, rotational constant, rotational term. Okay. So now let's see what happens if we absorb radiation. First, let's make a plot. And vertically, I'm going to plot Ej over Hc. In other words, I'm going to plot the rotational term, depends on J. So if J equals 0, we can plug in. Let me just simplify this now. This is equal to so the rotational term is Bjj plus 1, pretty simple. So obviously, if J is 0, this evaluates to 0. If J is equal to 1, this evaluates to 1 times 1 plus 1, that's 2b. If we substitute J equals 2, this becomes 2 times 3 is 6. Right? And maybe I can sort of fit one more on there. If J is equal to 3, we have 3 times 4 is 12. That should be a little longer, but that's the best I can do. And I guess I had these. If you see a B without the tilde, that means usually they're using energy units instead of wave number units. So now let's think about the selection rule for absorption. So delta J is plus 1 for absorption, minus wave for emission. But let's just think about absorption. So that means that if we begin in J equals 0 and absorb some radiation, delta F is equal to 2b minus 0, which is 2b. Right? Now let's think about what happened when this molecule was excited. Is there a question?
No.
Okay. So a photon came along and was absorbed. And that photon had some energy. It also had a frequency and wave numbers. So remember, we write the frequency and wave numbers as nu with a tilde. Right? This is the nu of my photon. So what we find is that the photon has this same. Well, that's that. Yeah. So now let's. So that's one transition. Okay. Now what happens if we begin in the state 1, J equals 1, and go to J equals 2? What is delta F? I guess what I wanted to say is, when the photon is absorbed, then the change in energy in the molecule in wave number units has to be equal to the energy of the photon in wave number units. That's what I was getting at. So, so delta F is now 6b minus 2b. Which is 4b, and so that's going to be the frequency of the photon. Right? And up here, if we do this transition, j equals 2 to j equals 3. I didn't put what j was, but it was 3 here. Pretty straightforward, right? So let's now think what that's going to give us in terms of a spectrum. So let's just sketch out, cartoon-like, what the spectrum is going to look like. So we need an axis. Let this be the new axis where the frequencies absorbed. And we're going to get a peak here at 2b. And we're getting another peak at nu equals 4b. And another peak at nu equals 6b. And I didn't tell you what happens if you include j equals 4, but I think you maybe can get the idea. Notice the difference here is 2b, and the difference here is 2b. And in fact, if you do the math, this turns out to be 8b. So what you notice is that delta nu, and by delta nu I mean the difference between two consecutive frequencies, is equal to 2b. And that's pretty cool, because when you take a spectrum, you can measure the frequencies of the peaks, and all you have to do then, if you want to know B, is measure the spacing of the peaks, because B turns out to be that in turn is pretty cool, because B is related to, as we said, the moment of inertia. So this is so if we want to know the moment of inertia, well, you just have to do a little algebra, right? Yeah. So I guess one could invert this. And then from the moment of inertia, since the moment of inertia is equal to, this is actually 1/2 mr squared. Which is the same thing as mu r squared. That's really what I'm getting at. So from this you can get R, right? So R so that's pretty cool. You can get, from a spectrum you take, you can figure out the equilibrium bond distance. Sometimes we call this R sub E, it's the same thing. Questions?
My back is killing
So I'm going to show you now a picture of a typical microwave spectrum, because I think you might like to see it too. Nicer picture like this. There we go. So typical spectrum, you just notice the peak spacings are pretty equal. You'll notice the intensities are different. That's another story we'll talk about in a little bit. All that's there. This is a fun, I think a nice diagram. It shows you the transitions that are responsible, the transition that is responsible for each peak. So on top we have the energy levels, and at the bottom we have this is transmittance in this case. So this peak comes from the J equals 0 to J equals 1 transition, this from the 1 to 2, 2 to 3, and you can see why you see graphically very quickly why you get different frequencies. The spacings of those between the different levels, they increase as the levels go up. Yeah, so that's that. Just sometimes you'll see this expression for B where they use an H bar. I wrote a different one. If you write H bar as H over 2 pi, you get an H on top and an 8 down here, and you get an extra pi squared. It's same thing either way. So same equation. Yeah. That just shows you how you would get B. And this is for HCl. So notice I just took 2 consecutive peaks, the difference, 1/2 of it gives me B, and then from B I can get I, and from I can get the equilibrium bond distance. Yeah. So I wanted to talk about a few aspects of the spectrum that we haven't discussed so far, and one is temperature, oddly enough. So from that spectrum and from all the different intensity of the lines, you can actually deduce the temperature of the sample from which the spectrum was taken, or you can approximately deduce it. And that's pretty cool. Very often, if you have a sample, you could just measure the temperature of the sample, and you don't need to look at the spectrum to figure that out, right? But what if you get a signal from a star several light years away? You can't go and measure the temperature of the star with a thermometer, but the spectrum can tell you the temperature. And I want to tell you how that would work. So here's our reference sketch of a spectrum. Although we just saw it, it's good to have it in front of us visually, I think it helps me. Now what you'll generally find, if this is increasing frequency, what you'll generally find is that at low frequency the intensities, maybe that's absorbance, okay, but anyway, the intensity is small, and then it increases, goes through a maximum, gets small again. It's a general trend. So it's from these patterned intensities, that's how we can get the temperature. And I want to explain how. So we need to know a couple of things that you can say are factoids. But the intensity is going to depend on really two things. One is the transition dipole moment. That's an equation that I told you last time we can't derive because it requires time-dependent considerations, but I did show it to you. And the symbol for the transition dipole moment, we'll just leave it at that. And I will ask you to believe that the intensity is going to be proportional to the transition dipole moment squared now this mu naught is the permanent dipole moment of a molecule. So that I just have to ask you to believe. Now there's something else that I is proportional to. So I didn't leave everything in there. It's also proportional to the population of the level. So if this is J and this is J plus 1, and we're making a transition from J to J plus 1, then if there are lots of molecules that have quantum number J, then the transition, the signal will be strong. If there are only a couple of molecules, the signal will be small. And we saw earlier that the distribution among the different J levels will be described by the Boltzmann distribution. So, what's the Boltzmann distribution? It's the density, it's the degeneracy for state J times this. So this is the population of state J. I should say level J. Boltzmann distribution. So let's think about this. Let's simplify this first. Let's substitute for this dipole moment. So that gives us now let's think about the degeneracy of state of level J. Can anybody remember or figure out what the degeneracy would be? Let me give you a hint. The energy
2J plus 1?
Yes, 2J plus 1. Very good.
Oh my gosh.
Well, let's do it in terms of F. It's just easier. Right? BJJ plus 1. Well, there's another quantum number. There's J and there's also M sub J. And just to remind you, if J is equal to 0, M sub J is 0. If J is equal to 1, we can have 0 plus 1 minus 1. 2, 0, plus or minus 1, plus or minus 2. And if you just count all these, you'll see that the number of states, right, for example, this is 1, 2, 3, 4, 5. That's twice 2. That's twice J plus 1, because J is equal to 2. Okay. So the degeneracy is 2J plus 1. That's the point. So let's substitute 2J plus 1 here. E to the minus. Now I want to use my quantum number, so this is going to be HCB times J plus 1 all over KBT. This is just the energy. Right? The HC converts us from wave number back to joules. And then we got the B, and then we have JJ plus 1. So that's that. Okay, and this is really all, well, that's fine. What good is that? Well, if I asked you to figure out the maximum in a function, what would you normally do? Take the derivative and set it equal to 0. Can we do that here? What's the problem?
Very, very complex.
J is not continuous. J can be 0 or 1 or 2 or 3. How do you take a derivative? You can't. So what we do is that we pretend that J is continuous, and we say, well, I mean, if these are closely enough spaced, then that's not such a bad approximation. If J were continuous and all these equations applied, then what would the value of JP be for the maximum? So we pretend, okay. Pretend J is continuous. And we don't pretend, we know what we're doing, we just define a function that is like J, but it's continuous, and so we see what happens. And we set dIdJ equal to 0. So we have to take the first derivative. So the first derivative of this is what we need. I wrote this wrong. I'm sorry for your notes. This should be a 2J plus 1. Make sure I'm right. Second. Yeah, this should have been 2J plus 1. So this cancels that, and we're left with, let's just simplify this first. I'm not going to write down again, it's out again, it's just the same as this. Okay, I just don't want to write it again. Same as this. Okay. So that's fine. So what happens when we take the first derivative? We're going to get some constant that includes the mu 0 squared. This was just proportionality, right? And now we have to take the first derivative, I'm sorry, I just better write it out and not be hasty like that. It's too confusing otherwise. Okay, so what happens when we take the first derivative? First derivative of J plus 1 is 1, right? The mu naught squared is just a constant, it's involved, it's part of this constant, who cares? Okay, so we're going to have the 1 times the whole exponential. Okay. So I took the derivative of this and multiplied by the exponential using the chain rule. Alternatively, I can just leave this in there and multiply it by the derivative of this. Well, the derivative of this is the derivative of the exponent times the exponential. So this gives me negative HCB. Now this is J squared plus 1, so the derivative becomes just 2. I'm sorry, this is not J squared plus 1, this is J squared plus J. So the derivative becomes 2J plus 1. Okay. So now we have 2J plus 1, and then divided by KBT. Okay. So that's fine, let's just simplify that. Yeah. There's all of that times then I forgot the exponential. It had to be in here. That didn't go away. So we still have the exponential. Okay, so that looks gross, but notice that all of this has to be equal to 0. And the only way that can be, the whole expression can be equal to 0 is if this itself is equal to 0. Now I know it looks hairy, but notice, let's just look at this for a second. Now this is the value of j that satisfies the expression this equal to 0, that gives us j max. And j max we get actually by looking at the spectrum and counting, right? So there's j max. Right. So this is for the transition from j equals 0 to j equals 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. So j equals 4 we're talking about here. So that's cool. So we can simply substitute a 4 right there. B we already know. The only thing we don't know is the temperature. So let's take this out and solve it for temperature. So what we have is that 1 equals, because all of this is equal to 0, 1 equals or solving for temperature,
You said j plus 2, shouldn't it be 2j plus 1?
now let's remind ourselves, this is from the maximization process, so this is actually j max in this expression, also up here. So in our little example here, we simply count, and we find, okay, j max is equal to 4. We know it. We know h, we know c, we know Boltzmann's constant, and we get b from the spectrum. The spacing of peaks is 2b, so we know that. So that's a derivation. You don't have to memorize the derivation, but it's really cool that you can, and I think that by measuring the maximum and measuring b, you can figure out the temperature. This kind of thing is used in astrochemistry or astrophysics to determine the temperatures of celestial objects that emit light.
I just wanted to know that you purposely went from 2j plus 1 to j plus 2.
Okay, what did I do? Let's make sure we get it right here. We're taking the derivative of this, which is 2j plus 1 like this, and then I went and I transposed it very cleverly because I was testing the other. I'm kidding, I just made a mistake. Okay, thank you very much. Okay. So anyway, that's another thing you can do with spectroscopy, temperatures of distant things. Any questions about that? Okay. So I basically expect you to know that, you know. I'm gonna have to give you the formula for you to apply it. Otherwise, you know, what would you do? Just know that you can measure temperatures from spectra. Okay. I want to erase this and talk about something else. Okay, to erase? By the way, I modified the slides just a little bit this morning. I'm always trying to perfect things, and so then I uploaded those just before class. If you uploaded them last night, you have something slightly different. It just is missing a few things. I'll leave that there. So the next topic is a refinement of the expressions we've introduced already. Okay. Centrifugal distortion. So we imagine some poor molecule can spin about an axis, and there it is. It's spinning. Now we have an expression that we already introduced for the energy of that molecule, right? We said the energy depends on J, and it's equal to but right now I actually need full expression for B, so let's see, J plus 1. So let's go back to this. I'll put it that way. Okay. Now imagine our molecule is spinning because it's rotating, and imagine that that rotational quantum number gets pretty big. So far we've assumed a rigid molecule that cannot stretch, right? It's just rigid, we call it a rigid rotor. Well, in fact, the molecule's got a force constant, those bonds can't in principle stretch. What's going to happen to the length of that bond as you increase the speed of rotation? It's going to increase because of centrifugal force, a pseudo force, centrifugal force, right? That's exactly right. The bond length is going to get longer. So when we recognize the way I wrote that if you take into account the fact that the bond length gets longer, is the energy gonna, how do I want to put this? If we take into account the fact that the bond increases in length as J goes higher, is that going to change the energy expression in a positive way or negative way? Negative, because notice the R squared is in the denominator. So our expression for energy is too large. It needs to be modified. So we're going to introduce a new constant. And it turns out it's proportional, this change is proportional to something, and I can show you what it is. So now we're going to modify this for centrifugal distortion. Well, let's go ahead and let's also change units to F of J because it's the better frame of reference. So this will be I like to write it this way, although you'll find it's usually written as J squared times J plus 1 squared. Right, I just multiplied it out. This new constant is called the centrifugal distortion constant. Has to be measured for every molecule. Notice the negative sign, that's because of what we expect, a reduction in the energy. Okay. One could, of course, have left this positive and defined D as a negative number, but for tabulation purposes, we prefer to define D as a positive number, so we need the minus sign. Okay. D is different for every molecule. So now D turns out usually to be a much smaller number than B, and I've got an example here to show you somewhere. Oh yeah. for HCl, that's 4.1 times 10 to the minus fifth. So you can see that D is much smaller. Questions? 2 footnotes then. First, if you want to, you can think of these as the first 2 terms in an exact expression, and the exact expression would be a power series. You know, a function can be something times x plus something times x squared plus x cubed and so forth. So these are the first 2 terms where the thing being taken to some power is j times j plus 1. Okay. The next term would be j plus 1 cubed, j plus 1 to the 4th. So if you read the spectroscopic literature, where they often take very highly resolved spectra and then fit to polynomials, they can extract many, many more terms. Not every term has a simple physical explanation or interpretation, but this second term does have a simple physical interpretation, centrifugal distortion. That was footnote 1. Footnote 2. I want to introduce a new term. Maybe it's not new to you. 35Cl is a particular isotope of carbon, right? It's an isotope.
Oh.
H1 is a particular isotope of hydrogen, protium we call it. Okay. Here are a couple other mixtures. Okay. H137 chlorine, right? Chlorine 37. We could have a hydrogen with a proton and a neutron in the nucleus. It's still hydrogen. We call it deuterium. So you can imagine all of these. So each of these individual atoms is an isotope. There's one isotope of hydrogen, another of. It would be incorrect to call 2H37Cl an isotope. It's a molecule composed of 2 particular isotopes, right? So the term we have for molecule, when you specify the isotopes of every atom, is isotopomer. Okay. Isotopomer. So just get that. It's just confusing when you call this an isotope. It's an isotopomer. Okay. Questions? Okay. Check the time. Oh yeah. I wanted to tell you before I leave this topic that there's a useful approximate expression for the centrifugal distortion potential that you may see. I need to explain this though. The B on top is obvious, right? That's the rotational constant. What's the thing on the bottom? Okay. It's not the frequency of absorption when there's a transition. That's not what it is. This is the vibrational. It's the vibrational frequency. So. Remember how we say that of the vibrational frequency is 1/2 pi times the square root of force constant over mu. Remember that? Okay. So we've just changed units and gone to wave number units. That just adds the HC, but we still have the proportionality to. Okay. So what this is saying is, notice if the frequency is high, that must mean that the bond, the force constant is large. Larger the force constant, the larger mu. Now you can imagine if the force constant is large, then you're not going to distort very much when the molecule spins fast, because that force constant prevents it, right? So the larger the force constant, the larger the frequency, and the frequency goes down here in the denominator. This is the vibrational frequency related to the bond force constant. So that's a nice approximation. You'll see we can get this from our IR spectroscopy. We'll see that next time. And this from microwave spectroscopy, and you can estimate that. Okay, so then if there are any more questions, I want to go to the different kind of spectroscopy. I want to talk about the process of light scattering. Then we can talk about Raman spectroscopy. So I'm going to erase all of this. So we know what absorption is. Photon comes along, gets absorbed by a molecule, and the molecule changes its energy. In light scattering, something else happens. A photon of with a particular energy encounters a molecule, and it gets scattered. And the scattered light often has a different frequency than the incoming light. So in other words, in the scattering process, see, I want to write this down. So what this says is that the energy of the incident photon plus the plus the initial energy of the molecule has to be equal to the energy of the scattered photon, new final, plus the final energy of the molecule. So there's another way that people often portray this. So I'm going to show a picture to help that. Ouch. Oh, I'm sorry about that. Oh, that's me. I'm sorry. That's me. Oh, that was another thing. Okay. So this is sometimes portrayed this way. This picture, I call it a helpful crutch for understanding what happens in So this has got a mistake on it. Let's correct it. I'll correct the slides. We'll talk about the selection rule in a second, but the selection rule is different for Raman scattering. So the selection rule for Raman scattering, I guess I'll say for a linear molecule, is the gross selection rule we're going to talk about in a second. So I'm going to leave it blank. But the specific selection rule is delta J equals 0 or plus or minus 2. Not going to try to explain that comes from the transition dipole moment. The text gives a picture and an explanation that just doesn't quite make a whole lot of sense to me. Maybe I haven't thought about it right, but I'll just leave it as a given, right? For the specifics, this is for a linear molecule. If it's nonlinear, then you can also have plus or minus 1, but that's in your text. I guess I should put that. Anyway, this is the crutch. You can think of the scattering process as a photon absorbed and then a photon emitted. Thing is, it really happens at the same time. So, but it's a nice crutch. The question is, though, what level is the photon excited to, and then to what level is the photon excited and then fall back from? And the answer is we don't really know. It's a fictitious process. But we speak of a virtual level, which is whatever you want to picture the photon excited to. It doesn't really matter. Virtual level because this is fictitious. Right? But you can think of the incident radiation as exciting you, and at the same time, a photon is emitted as you fall back to some level. Now there are three possibilities to where it falls back. One is it falls back right where it started, delta J is 0. That's going to be your strongest signal. Second possibility is that it's excited way up and it falls back to a J plus 1. Right? In that case, notice the frequency of the scattered light is less than the frequency of the absorbed light. Remember, the length of the line is proportional to the frequency of the light. So the longer the vertical line, the higher the frequency. So we call this Stokes radiation. So Stokes radiation is at smaller frequency than the incident radiation. The other possibility is that delta J is -2. We call that anti-Stokes. And now the frequency of the scattered light is larger than the frequency of the incident light. So let's take a brief look at the diagram for a Raman spectrometer. So you've got a laser, some focusing lens, you've got a mirror, and here's your sample. Now the thing about scattering is that, well, if this were absorption of light, then the light, then all you would have is this signal, but some of the radiation would have been absorbed by your sample, right, somehow. The sample's here, and there's also a mirror. The picture's a little funny. Okay. Scattered light, though, is emitted in all directions. Okay. It's not simply absorbed in along the direction, of the. It doesn't simply change the incident light. You have scattering in all directions. Only some of those directions are shown here. It's scattered 360 degrees. But if you have a focusing lens here, you'll capture all the light that goes through that focusing lens, and if you focus it, then you can, you can detect it and so forth. And then you can measure the frequencies absorbed. Now, the thing about Raman is it's really weak. So the scattered light that is not the Rayleigh light is really low in intensity. So it takes a pretty highly resolving a high sensitivity spectrometer to get the spectrum. Okay. So that's sort of the principle. Now let me tell you the gross selection rule. I'm going to use, yes?
If the photon is leaving at a different frequency than the original, what is that energy being converted into?
What is the energy converted into? It simply is transferred to the molecule.
Vibrational rotation.
It's converted into rotational energy. So in this case, the photon lost light, the scattered light, the photon lost light as it was lost energy as it was scattered, and that energy was used to raise the rotational energy of the molecule. Here, the photon gained energy, and the molecule lost energy, rotational energy. Yeah. So, here's the gross selection rule. The molecule must be anisotropically polarizable.
What?
Yeah, I know. Okay, I'm gonna write the word down and then I'll explain it. Anisotropically,
polarizable.
which has nothing to do with what latitude you're making the measurement at. Tropically polarizable. What the heck? So, first the idea of polarizable. So, if I'm a molecule, then I've got nuclei and I've got an electron cloud around the nuclei. And that electron cloud can in principle be distorted. Right? And that will be distorted, for example, if the molecule interacts with light, because light carries an oscillating electric field. And when that electric field encounters the molecule, well, the electrons are polarized. I mean, the electrons are charged, so they will interact with that incoming oscillating electric field, and the electron cloud can become distorted while the photon is there in the vicinity. Okay, that's cool. So then the question is, suppose that my photon's coming this way. Well, it's going to interact with the field, with the molecule in a certain way. Actually, this is a better picture. If the electron's coming this way, notice its electric field is oscillating perpendicularly. Let me draw a picture. Here's my little photon, poor guy.
Poor guy.
Yeah, he's moving this way. We'll call that X, right? The electric field is oscillating in the Y direction. If I let this be Y, right? Perpendicular to the direction in which the photon's moving. So let's look at this. So if my photon is in this direction, the oscillating electric field's in that direction, and it will cause a distortion in the electron cloud. Suppose now, though, that the photon moves in this direction, then the electron field is oscillating like that, and we get a distortion like that. Now, the question is that distortion going to be the same as that distortion? Is that distortion going to be the same as that distortion? Depends on your molecule. If your molecule is methane, CH4, it turns out it's spherically symmetric, and it doesn't matter what direction the photon's moving in, the polarizability is the same. But in this case, the polarizability is not the same in these two directions. So if the polarizability is independent of the direction of the electric field, we say that the molecule is isotropically polarizable. Doesn't matter what the direction of it. But if the distortion depends on the electric field's direction, we say it's anisotropically polarizable. And that's what's required for scattering of light. So the gross selection rule is that the molecule be anisotropically polarizable. It may not always be obvious to you from looking at a molecule whether the polarizability will be isotropic or anisotropic. Sometimes you would have to be told or just have deeper knowledge. But you should be able to understand and predict that CH4, anything with that degree of symmetry, isotopically. What's cool about this is that for a linear molecule, even if it's H2, it has no permanent dipole moment. But I think you can see from the way these are drawn that they'd be representative of H2. Even a homonuclear diatomic is anisotropically polarizable, and therefore Raman active. So that's pretty cool, because with Raman now you can measure the bond length of H2 or O2 or something. You couldn't measure those molecules' bond length with microwave spectroscopy. They're microwave inactive because they have no permanent dipole moment. Questions? Yeah.
You said if it doesn't matter the direction it moves, so for example, CH4, you said it's spherically symmetrical. that is isotropically
Correct.
polarizable,
Isotropically polarizable.
which is not active.
Right, right. Okay. So we got a cool way to measure bond lengths properties of even homonuclear diatomics, and that's the cool thing. What does the spectrum look like? Well, here are the selection rules for linear molecules, right? Gross and specific. What does the spectrum look like? It looks kind of like this. Here we've got superimposed the spectrum itself downstairs, and then for reference, upstairs are the energy levels of the molecule, the rotational energy levels. Okay. Now notice the lengths are 2, those little top arrows are 2. That's because delta J is plus or minus 2. Here we've got the Stokes lines. Delta J is plus 2. That means the molecule gained energy, but therefore the light lost energy, lost frequency. That's Stokes. Here we've got the anti-Stokes. Delta J is negative 2. And then the Rayleigh line, it would be a little, it wouldn't be exactly a line, but very narrow, is pretty strong, stronger than it looks here. This is schematic. That's the Rayleigh scattering. Delta J is 0. Okay. The Rayleigh doesn't tell you much about the structure, but the Stokes and anti-Stokes do. Now the spacing between the peaks is not 2b anymore, because now delta J is 2, not 1. Instead, the spacing is 4b. But you can use that then to calculate the equilibrium bond length. Yeah.
Why is delta J2 here?
Because I told you so.
Okay.
So, yeah, so Raman spectroscopy has different selection rules from microwave spectroscopy. The transition dipole moment is different for scattering than it is for absorption. It's another way to put it. In terms of a physical property you can grasp, you know, there are some explanations in your text you can try out. They never quite clicked for me for Raman spectroscopy. They kind of clicked for me for microwave. But maybe you'll get insight from them. That's super. But I can't present something I don't understand. So that's that. Sorry.
Congratulations. Congratulations. Me too.
So, I have 2 more stories to tell. One I can tell very quickly because we're only going to tell at the surface level. And the other I'll tell next time, I'll begin with, and then we'll proceed to the infrared spectroscopy. One story I want to tell is called the Stark effect. I think I maybe mentioned it. Mu right here is the permanent dipole moment of a molecule. And what I'm saying with this equation is there's a way to measure the dipole moment of a molecule. You might not really care what the dipole moment is of a molecule, but there's a lot you can do with these dipole moments that's useful. And for the biochemists, for example, good God, just for example, some are involved in the docking project that we've been working on in undergraduate research, but we build molecules of proteins and RNA and DNA and lipids and everything in order to understand how they interact with ligands or with each other. To build those molecules, we need to know the partial atomic charge of every atom, as well as we have to parameterize the van der Waals interactions and all sorts of other things. If we want to figure out the partial charge on atoms, how are you going to do that? Well, measuring the dipole moment is one way. From the dipole moment, you can get at what the dipole moment together with the bond length, and you can figure out the partial atomic charges. And from that, you can, I won't say you can cure cancer, but you can do very powerful things like these docking and things. So we can model the protein folding problem to get somewhere. So that's a good thing to be able to measure, that's what I mean. Well, it turns out that if you place your molecule in an electric field, then the rotational energy levels get shifted. Before, they did not depend on the quantum number m sub j, and now they do. We use the capital M in this context. I'm not going to derive this because it actually is pretty sophisticated and it's beyond what we can do. But I'm simply telling you that the resulting expression depends on capital M sub j. A is some constant that depends on J and M sub j, and you can see with these two. The E here is the magnitude of the electric field. So that's a pretty cool thing. This is the kind of shift you're going to get. So here we have the energy level with the field off. Then all of these M sub j levels, if J is specified, all the M sub j energies, they're all degenerate. If you turn the electric field on, which means if you take your sample and you put it in an electric field, then this is how the field shifts. And because the levels are now different, you can absorb radiation. There will be selection rules, but you can absorb radiation for changes in M sub j, and then you can get it what the splittings are, and then you can backtrack and get the dipole moment. So I think that's pretty cool. You get distances, dipole moments, just from shining light on stuff. This is a footnote. The other stuff's more important, but you should know this is possible. So that's an introduction to spectroscopy. Notice today that we made reference to two different physical processes: absorption of light, scattering of light. We stuck our sample in an electric field to do one thing. We do anything we can to be clever and learn more information. So I have one more footnote to tell you about Raman spectroscopy. It's important because without this footnote, you can misinterpret spectra. But I'll talk about that at the beginning of the next period, and then we'll go on to infrared spectroscopy. Yeah?
So do the equations that apply for microwave spectroscopy also apply for Raman as well? For finding, for example, B and I as well? Except B is now slightly
They'll all
off,
apply except that the spacing between two energy levels is now 4B instead of 2B. So, but everything else is just the same. Yes?
Maybe I'm understanding.
Here?
Is this similar to the Zeeman effect? Are they related?
Yeah.
What's the